Our next section in probability is going to talk about how to find independent and dependent events. So first, let's define what is an independent event. It sounds basically exactly like what it is. An independent event is when the occurrence of an event does not affect the occurrence of another. So you're thinking about questions like, if you have a deck of 52 cards, does drawing a king on my first draw affect my chances of drawing a queen on my next draw, sort of thing. So we want to be able to tell if events are independent. So to tell if events are independent, we're basically checking a product. So what we're looking at here is you're checking two things. The probability of two events A and B are independent if and only if the probability of A and B is equal to the separate probabilities multiplied together. So we're looking at, for example, example 1, a bag contains 6 pieces of paper, numbered 1 through 6. A student randomly selects a piece of paper, replaces it, and randomly selects another paper. What we want to do is determine if randomly selecting an odd number, a 5 first, and then selecting an odd number second are independent events. So we have two things happening, the probability of A and the probability of B. So we can define A as selecting a 5 first, and then we'll let B be selecting an odd number second. Okay, so what we want to do then is we want to figure out the probability of three things, A and B both happening, and then A and B separately. So if you looked at the directions, it says to use a sample space. So we want to use a sample space to determine whether or not our events are independent. So when you see that sample space, what I want you to do is I want you to make sure you've listed out all the possibilities. So you might want to, do a tree diagram or list out all your possibilities, but we want to determine all outcomes. So let me go ahead and write down my sample space if you want to try that out yourself as well. Let's see what we get. All right, well, hopefully you found that there were 36 different options because if you notice, we are replacing the paper. So if you draw one first, you're putting that one back and you can draw it out again. So you have a total of 36 different options. And remember, to check if it's independent, we want to see what's the probability of A and B happening, and then what's the probability of A separately and B separately, and we're going to multiply them together to see if it checks out. So why don't we look at that joint probability first? So if we want to select a 5 first and then an odd number, what would that be? Well, if I want a 5 first, then I'm only looking at this row and an odd number, which means I have 5, 1, 5, 3, and 5, 5. So that means I have 3 out of 36, and that reduces down to 1/12. So again, that was our joint probability, A and B put together. Okay, so then what we want to do is we want to check, does the probability of A separately times the probability of B separately also equal 1/12? Because if it does, then we have independent events. So now let's take a look at what's the probability of just A, selecting a 5 first. Well, then we have 1, 2, 3, 4, 5, 6, right? So those are all the possibilities of selecting a 5 first. So then we get 6 out of 36. Okay, and we know 6 out of 36 reduces down to 1/6. So then our last component then is finding out the probability of B. So the probability of B is selecting an odd number second. So it doesn't really matter what the first number is, but what's the possibility of selecting an odd number second? Well, then we look and we have here 1, a 3, right, a 5, then another 1, then another 3, then another 5. And go ahead and finish this off and you guys tell me what is the probability of B. So hopefully you figured out there are 18 possibilities of picking an odd number second. So 18 out of 36 then reduces to 1/2. So the final thing we need to do is double check if it's independent. So remember, it's independent if and only if the probability of A and B, which we got as 1/12, is equal to the probability of A times the probability of B. So let's go ahead and check that. Is 1/12 equal to 1/6 times 1/2? Well, the answer there should be yes. Right, so just make sure you show me that work, and then we'll see that 1/12 equals 1/12 equals 1/12. Check. So then we can say that these two events are independent, right? Selecting a 5 first and selecting an odd number second do not affect each other. All right, so just make sure at the very end you state your findings, right? So that randomly selecting a 5 first and randomly selecting an odd number second are independent events. Okay, so go ahead and try example 2, same idea, checking for independence with this group of 4 students. But keep in mind that once a person is selected, you can't reselect them. So if you select a boy first, then there are no boys left to select second. Okay, so keep that in mind and think about how that affects your sample space. Go ahead and try that, and then let's come back and check. Oh, don't forget to write down your whole sample space too. So as you're working, double check your sample space. We should have a total of 12 possibilities because you can't do girl one, boy, boy, right? So think about that as you're checking for independence. All right, well, hopefully you got not independent, and as always, check my math, but I do want to see all of this work. So I want to see you show me how to calculate the probabilities, right, and the check for independence, and also your final conclusion, your final deduction. So here they are not independent because you see the product doesn't equal that probability of A and B. Okay, so those are independent events. We also have dependent events and what it's linked to, conditional probability. And let's go ahead and define that. So if independent events mean the events don't affect each other, dependent is going to be the opposite. That means when the occurrence of one event affects the occurrence of the other. Okay, and then linked to that is the idea of conditional probability. So this is when you put a condition on it. So conditional probability is basically the probability of any event B happening given that the event A has already occurred. So an example of conditional probability might be you're looking for the probability a student picked at random is in Ms. Huang's class given that the student is a geometry student. So you're assuming first the condition that the student is geometry has already happened, and then you're looking for, who's in Ms. Huang's class, versus just the probability of any student out there is a geometry student. So you're kind of making a subset, okay? So these two ideas are linked. Conditional probability is also written in this following notation. So you'll see this probability with B and a vertical line A, that's read as the probability of B given A. So meaning A has already happened, what's the probability of B? So the condition is always the second part. So the probability what we're looking for is the first letter, right? The event B, given the occurrence of A. So how do we calculate or how do we determine if events are dependent? Well, there's an equation for this as well. So if you're looking at two events A and B, the probability of A and B should equal the probability of A times the probability of B given A for events to be dependent. Now connected to this, we can also solve for the conditional probability so you can determine what is conditional probability. So if we simply just divide probability of A to both sides, we can solve for the conditional probability. So then if I'm ever asking you to, for example, find the probability that a student chosen at random is a girl, given that the student is in Ms. Huang's first period class, right? So if you have that situation, then you know, oh, well, the event B is the student is a girl, and the event A is that they are in Ms. Huang's class. So then you can, work with that equation to solve for your conditional probability. Okay?
Now, before we move on to the examples, let's quickly just revisit example 2 and talk about dependent events, because this looks very similar to independent events because you're going to multiply two probabilities, but what changes is the second probability. And if we take a look back at example 2, we can see this kind of in action. So let's kind of just revisit example 2. Okay, so if we want to actually find the probability that we pick a girl first and a girl second, given the situation where we're picking the one girl to be a speaker and another girl to we're trying to pick one girl to be a speaker and another girl to be a recorder, but you can't have the same girl do both roles. So if we're trying to do the probability of the girl first, picking a girl first, we're going to go back and say, okay, well, we had 3 girls and 1 boy, so 3 out of 4 is the probability of picking a girl out of the 4 total people. So now the second part is what's different from independent. So we're saying, okay, we took 1 girl out of the mix. So now that probability of B given A is just saying, okay, A happened, so what changes about our situation? Well, instead of having 4 total people, we only have 3 students left to pick from. So that changed, right? And if we already picked 1 girl and we want to pick another girl, how many girls are left to pick from? Well, we had 3 to begin with, but 1 already got chosen, so now there's only 2 left. So that's the idea of B given A, right? And then we can go ahead and multiply to get the probability. So I'm just going to cross cancel because I like doing that, but you can always multiply and simplify later. And with the probability of picking a girl first and then a girl second is just 1/2. Okay, so that is a quick revisit to example 2, just showing you how to calculate the probability of a dependent event, because the rest of these examples in this section are going to talk about conditional probability. So before we go on to the examples, just one last thing, don't get too intimidated by the language of everything. You might be wondering like, oh my gosh, what is this B given A business? It sounds so complicated, but really it's just saying, okay, it's the probability of the next thing after the first thing's already happened. So here's a nice example, I think, that we can all relate to, right? It's Halloween, you're out trick-or-treating, and you and your neighbor, right, are going together, and there's a bowl outside someone's house. You want to reach in the bowl and grab a piece of chocolate. So that's A. That's you have the whole bowl to pick from, and you're going to grab a piece of chocolate. Now, your neighbor is going to come up after you've taken one. And then you're asking yourself, I wonder what's the probability that my neighbor is going to also get a piece of chocolate, given that I've already taken one out. So what you're taking into account is there's 1 less piece of chocolate in the bowl. Now what's the probability that my neighbor is going to get another piece of chocolate, if that makes sense. So it's not saying there's anything crazy fancy about the condition. It's just saying let's take into account what already happened and adjust our probability for the next outcome, right? Okay, so let's move on to example 3. So we have a quality control inspector checking for defective parts, and the table shows the results of his or her work. We want to find the probability that a defective part passes. So if we want to rewrite this using probability notation, what you want to see is, okay, we've got basically conditional probability happening. If you're not sure, I'll show you how this works. So ideally, right, we want to know what the probability of a defective part passing is. So you're like, wait, there's a condition here. This part can't be any old part that passes. It's got to be a defective part that passes. So this is my condition, right? And then what I want out of that condition is I want to know, okay, what is the probability that it's going to pass? So when we write this, this is the probability of a part passing, given that, that's what that vertical bar means, given that it's defective. Okay, so if you want to go back and look at your conditional probability kind of formula, which we had earlier here, the probability of B given A equals the probability of A and B over the probability of A. That's basically this, the probability that we have a part that passes, or actually let me write this consistently with what we had, right? It was A and B. So the probability that it's defective and passes, oh, excuse me, that's so ugly. All right, passes over the probability of the condition that it's defective. And we can read that from the table. So what's the probability that it's defective and passes? Well, defective and passes is 5 out of our grand total of, and you can just add up all those 4 numbers to get 246. Okay, so my numerator here is going to be a fraction 5 over 246 over the probability that it's defective. So how many are defective? Well, that's these two put together. That's going to be 29 out of 246. So my denominator is 29 out of 246. Now don't be freaked out when you look at this. It's a fraction inside another fraction, but you can always go back to what you've been doing with fractions before, you can divide 5 over 246 divided by 29 over 246 and keep change flip. Or remember this handy trick. If you have two fractions with the same denominator, we can just basically cancel out the denominators, because when we multiply by the reciprocal, the 246's will cross cancel. So that is just 5 over 29. So that's how that conditional probability formula works. Now, do you have to use this? No, especially when you're given a situation like this table. So I'm going to go ahead and erase what I've marked here. Because when you're reading this table, what's even easier is if you look at the intersection of defective and passes. And defective and pass are just these 5 people. And because we know or 5 parts, right? And because we know we are only looking at defective, we don't care about the rest. So alternatively, what you can do is you can just say, hey, we have 5 of those 29 defective parts that are going to pass. And go ahead and read the table. I don't care how you do it, as long as you get it. Now I showed you the formula, the fraction over a fraction, because there are times where you won't be given the table, where you might actually have to do the calculation. Okay? So that is part A. So now I'd like you guys to go ahead and try part B. So same idea, pick your method. Personally, I would read the table because I'm given the table, but it doesn't hurt to practice using the formula either. But pick your method and let's go ahead and come back and check. All right, so hopefully we all got 208 over 217. That doesn't simplify any further. So we can leave it like that. Remember, just look at the directions. If it does ask you to round, please do round to the correct place value. But here it doesn't ask, so we're going to leave it as a simplified fraction. Okay, so our next example is an example where we don't have a chart to read. So this is what I was trying to say earlier. Sometimes you do have to use that formula. So what we have to be very careful of with here is when we're dealing with dependent events, especially with conditional probability, is you want to really be clear about what the condition is, because that would be the probability we're putting in the denominator. It's really easy to tell what the two pieces are, like defective and passes or non-defective and passes. That's going to be the numerator, but the denominator has to be the specific condition. So if we don't identify the condition, we're kind of in a lot of trouble. Okay, so let's read through example 4. At a clothing store, 75% of the customers buy pants. Only 20% of the customers buy pants and a belt. What is the probability that a customer who buys pants also buys a belt? So you're thinking, okay, what is it about this customer that I want to know will definitely happen? And then what is it I'm looking to happen on top of that, if that makes sense? So if we're asking, what is the probability that a customer who buys pants also buys a belt? We're saying, okay, well, this customer's already bought pants. There's my condition. Right? And then what we also want to check is, will they also buy a belt? So I'm just going to call this that B probability, right? So we have that condition, which we called A, and we're looking for the probability of B given A. So remember the formula? The probability of B given A is the probability of A and B over the probability of just A, which is your condition. So now we want to read through the problem and say, okay, what do these percentages actually mean? So what is this 75%? Well, 75% are the people who buy pants. So that's my A. So that's going to be my denominator. I'm going to change that to a decimal. And then 20% buy pants and a belt. So pants and a belt, that's A and B. Right? This is A and B. So that's going to be my numerator. And once I have that information, so I'm just going to convert that into a decimal as well, 0.20. There it is. And all we have to do is simplify this, right? Easy way to do this if you don't have a calculator is just move your decimal places, right? So we can move the decimal place 1, 2 to the right, 1, 2 to the right. So that way all of our numbers are in the ones place. So 20 over 75. And then divide by 5 to get the reduced fraction, which is 4 over 15. And again, if you want to write this as a decimal value, if it asks you to round it to a specific place value, please do. Sometimes we like to match the formatting of the word problem with our answer. So if it gave us percentages, sometimes we might want to give that as a percent. So if you rounded that, that's about 27%. Okay, so that is conditional probability, the probability of B given A. All right, so last set of examples. Now we have to just in general find probability. So what's important here is you have to identify, is it independent? Is it dependent? And then how do we actually, or what do we actually multiply together? Because as long as we're dealing with an and situation, it's A and B, all we're doing is multiplying. So the question is, am I multiplying the probability of A times the probability of B? Or am I multiplying the probability of A times the probability of B given A? Right? Which is just a fancy way of saying the second probability depends on the first one, or the two probabilities are completely independent of each other. So if you take a look at example 4, as part of a board game, you're going to spin a spinner, which is divided in equal parts. So that means every part is equally likely, right, to be an outcome. Find the probability that you will get an even number on your first spin and a number that's less than 3 on your second spin. So the first thing I'm asking myself, okay, if my even number on the first spin is A, and a number less than 3 on the second spin is B, does A impact B? If I get an even number on my first spin, will that make it more or less likely I get less than 3 on the second spin? The answer to that is no, right? Just because we land on an even number first doesn't mean we take that number away or we've changed in any way that sample space. That's what you want to ask yourself. Did I change the sample space after A? And here, no, our spinner is still the same. So this is independent because we can still get B regardless of what happens in A, right? That B probability is going to be the same no matter what, if A happens or not. So this is an example of an independent event. So now if I'm looking for the probability of A and B, I'm just going to multiply the probability of A times the probability of B because they're independent. So remember, A is the even number on the first spin, and B is a number less than 3. So what you want to do is just look at each probability separately. So on the spinner, how many numbers are even? Well, 2, 4, 6, 8. So that's 4 out of 8 because they're all equally likely, 4 out of 8. Now, forget the evens, right? How many numbers are less than 3? 2. 2 out of 8. So that's the probability of B. What we're going to do is multiply them together. And there we have our answer. So nice and easy if it's independent. So that'll be 1/2 times 1/4, or just 1/8. So again, can't stress enough, the first thing you want to do is ask yourself independent or dependent. And how do you know? If you change the sample space after A happens. Okay? So, I don't know what happened to my numbering, but the next example says example 6 when I guess it should be example 5. Oh no, example 4 should have been 5. So this is right, example 6. Okay, so now 9 women and 6 men are on a committee. 2 people are randomly chosen from the committee members to serve as a chairperson and as a treasurer. Find the probability that both events A and B will occur. A, the chairperson is a man, and B, the treasurer is a woman. So again, start off with independent or dependent, right? So now we have to think, okay, A and B are defined for me right here. Does the outcome of A affect the sample space for B? Well, once I've chosen a chairperson, can that person be chosen again as a treasurer? No, right? When you look at your ASB elections, everyone runs for one position. No one's both ASB president and ASB treasurer at the same time, right? So this does affect the sample space because if you think about it, one person can't be both positions. So once we picked A, right, our total of 9 plus 6, 15 goes down to 14. Does that make sense? So now instead of having 15 people to choose from, once we pick the chairperson, now we're left with 14. So that is what we call a dependent event. So that means the probability of A and B is the probability of A times the probability of B given A, which is just a fancy way of saying now what's the probability of picking a woman out of the remaining 14 people. Okay, so again, let's start off, at the beginning. So the probability that our chairperson is a man. So we have 9 women, 6 men. So our total people are 15. So I'm going to put this over 15 because I had 15 to start with. Now, of those 15, how many are men? 6, right? Pretty straightforward for probability of A. But now the second one, right? Don't get confused by this. We're just saying, okay, now we've changed our sample space. So now instead of 15, we've got 14 left, right? So out of those 14 people, how many of those are women? We didn't pick any women first, so we still have 9 women left to choose from. So 9 out of 14 is a probability we're going to pick a woman out of the remaining 14. That's what that B given A means, right? So we're basically just adding and subtracting. So again, what's important is you're just saying, did I change the sample space? And once I change the sample space, I'm using the new sample space, right? Out of the 14 people, how many are still women? And then I make my new probability. And then from here, we just, again, multiply our fractions. So I'm going to simplify first, just to make my life a little bit easier. And then I also like to cross cancel. So I can see 2 and 14 will cross cancel. Remember, you can only cross cancel when we're multiplying, not when we're dividing, adding, subtracting, or if it's a proportion. But if that's confusing for you, don't bother. You can always simplify at the end. So 1 times 9 is 9, 5 times 7 is 35, so 9/35 is that probability. Okay, last example. So a bag contains 10 red marbles. Oh, and that should say and, sorry about the typo. And 5 blue marbles. You randomly select 3 marbles from the bag. What is the probability that all 3 marbles are blue when we have 2 different situations here? You replace the marble before selecting the next one. Part A. Part B, you do not replace each marble before selecting the next one. So before we even do these calculations, what I want you to think about is what's the difference between A and B? Because for all of these, we're selecting 3 marbles that are blue. So it's the probability that it's blue, and blue, and blue. So it's blue and blue and blue. So it's the same thing we're calculating, but 2 different situations. So remember, go back to think about the first probability and does it affect the second one? So if I take out 1 blue marble, put it back in, does that affect the total number of marbles in the bag? No, I'm still dealing with the same 15 marbles, right? 10 red, 5 blue. If I take out 1 blue and put it back in, there's still 5 blue in there, and there's still 10 red in there. So if we replace it every single time, we'll notice this becomes an independent situation. Because I'll take a marble out, put it back in, take another marble out, put it back in, no matter what, that bag is always going to have 15 marbles. Versus part B, we do not replace the marble, right? If we don't replace that marble, what's going on here? So it could be your friend A takes a marble and keeps it. Now you're going to go up next. Do you still have the same 15 marbles to choose from? No, your friend took 1 out. There's only 14 left. So that changed the whole thing. So now we're looking at a different total. Then you take 1 and now there's 2 less, and your third friend comes up and they have only 13 to choose from. So when we don't replace it, we're changing the totals. That is creating what's called a dependent situation, right? So those are dependent events. So now, how does that affect our calculation? Well, don't be intimidated by 3 things. It's blue and blue and blue. You'll be like, wait, Ms. Huang, we've only talked about A and B. It doesn't matter. We can continue linking things by saying it's A and B and C and D. No matter what, as long as it says and, we're going to multiply. So that means for this probability for A, we're going to find the probability of blue times the probability, the probability of blue times the probability of blue. So it doesn't matter how many things you link together with the word and, we're just going to multiply those probabilities together. So how many marbles are blue? 5 out of total 15. None of it changes as we go from one pick to the next pick to the third pick because we're putting the marbles back. So that is just going to be 5 out of 15 times 5 out of 15 times 5 out of 15, or 1/3 times 1/3 times 1/3, which is 1/27. Okay? So let's compare that to the dependent situation. So now what's just a little bit tricky about this is we have to just think about how the totals change, which isn't really a trick at all. You just have to think about it logically. You're like, I took 1 out, now there's 14. How many blue are left, etc. So we're going to look for, sorry about that. We're going to look for the probability of blue first. That one's easy because we've already done that. 5 out of 15, right? So what changes is Oops, I'm going to multiply. Now we want to find the probability of picking blue given we already had one blue. And then the third one, we want the probability of a third blue given we had blue and blue earlier. Okay, and if you don't recognize all that notation, that's okay. As long as you understand the situation, you're okay. So what we're starting with here is just using that fresh bag. You're the first one up. You have the whole total to work with. Blues are 5 out of 15, which is nice because we did that earlier. So now you're thinking, okay, what if I come up second and my buddy already took out one blue? Well, how many blue are left? 4. Out of how many total marbles in the bag? Well, we took one out, so 14, right? Then third person comes up and they're like, great, well, 2 blues got taken out. What are my chances? How many blues are left? Well, if 2 blues were taken out from the original 5, we've got 3 left. And if we got 2 marbles taken out in general, how many marbles left in the bag? Well, we had 15 minus 2, 13. So all we're doing is subtracting when we need to, right? And then we can just multiply those values. So I'm going to simplify earlier just to make my life a little bit easier, but you can always simplify at the end. So that'll be 1/3 times 2/7 times 3/13. And go ahead and multiply across the top, across the bottom if you'd like. If you realize we can cross cancel, you could totally do that because it's all multiplication. So I can cross off this 3 and that 3 since one's a numerator, one's a denominator. If you're like, whoa, that's some crazy trickery, don't worry, just multiply straight across the top, straight across the bottom, and simplify what you can. And we'll all end up with 2/91. Okay. Now, please be aware, do you always have to subtract from the numerator? No, it depends. So if I was looking for blue first, take one out and don't replace it, and then red, then I would do 5/15 times 10/14 because there's still 10 red left of the remaining 14. Okay, so just read through the situation carefully. Okay, last part to this, we want to compare the probability. So I don't want you to tell me like, oh, 1/27 is greater than 2/91 or something like that, but I want you to tell me what that means. And that's just basically a quick interpretation of what probability is. It's the likelihood. So in order to compare, I think it's a little bit easier to convert to decimals. So 1/27 is approximately 0.04. 2/91 is approximately 0.02. So in terms of likelihood, right, it is more likely for us to pick 3 blues in a row if we replace each marble before selecting the next one. So that's what I want you guys to do with these situations, or a problem like this where I'm asking to compare. Don't just literally tell me one number is bigger than the other, but what does that mean? Because in statistics, or I guess in statistics when we use probability and things like that, when we talk about probability, we want to talk about what it actually means. So we want to go beyond the numbers and we want to be able to interpret. So here, a very quick interpretation is, the likelihood is larger if we replace versus if we do not replace. Okay, so that wraps up this set of notes. Remember, if you have questions, please don't hesitate to reach out. Otherwise, thank you for listening.